Yeah, so today I will present two projects, mainly focus on the HumanPlus, which is a humanoid project. And if we have time, I will talk a bit more about MobileAloha. Um, Great. Can you guys see the presentation screen?
Yes, I can see it. It's pinned.
Cool. Yeah, so I'm going to first talk about HumanPlus. It's a humanoid project. Composed of two parts. One is the shadowing for teleoperation. One is the imitation learning part. So I'll first show what it can do after training with human demonstrations. So this is actual like normal size Nike shoe. It's not a like special skateboard. So all the things a humanoid do here is controlled by two new networks. One low-level policy, another is imitation policy. So before we dive into the the methodologies, I will first try to talk about how people used to teach humanoid user skills. So like there is traditional model-based control method where the perception is used to use for 60 post detection and prediction. Um, so this kind of approaches kind of rely on the humanoids, or the programmers actually need to pre-specify what kind of objects, what's the kind of model for that object to be able to have a pretty precise stop position estimation of the objects around the humanoid. And also there's, lately many methods that focus on purely using reinforcement learning, training simulation, and then inducing material. I would say both of these methods um, are very task specific in the sense that um, one kind of pipeline or setting or training will only solve one problem, one task. And also pretty much all of them relies on a post estimation in order to, fit the problem for model-based control and fit the problem, solve the problem of material transfer. And recently we have seen, from other commercial companies in the sense that people trying to integrate imitation learning into a pipeline. But most of them are, only standing still and pretty hard to do anything whole body out. And in comparison, human have very general skills in the sense that people have, can do cooking, play music, and doing basketball. Um, I take this kind of screenshot from the Eagle Axel 4D dataset. So one natural question people are, asking is that because humanoids looks very similar to humans, can we directly transfer, these kind of useful skills that humans have and all the kind of the data sets of human skills to directly to humanoids? The short answer is that it's pretty much impossible to directly just map or shadow the human motion to human noise. There are many reasons behind it. The first one is that humanoids and humans um, have very different actuation strengths and responsiveness. So compared to motor that's driven um, by a current loop or any kind of similar mechanisms, humans muscles have still very high instant responsiveness, and also the strength of it is very powerful compared, like much more powerful compared to normal humanoid actuators. And also, even though the humans and humanoids looks very similar in mythology, they still have very different degree of freedom. The length are slightly different, and the height and weight, all these kind of things are very slightly different. And also, humanoids and humans have different vision parameters and mechanisms. So when it comes to collecting data using egocentric vision, these kind of difference will come into play. And because of gravity, directly copying the joint angles from humanoids, from human data or human motion data to humanoids can be very problematic. So we kind of take the approach of training this kind of low-level policy that trying to map the human motion to humanoid motion that can be actually actuated on a real robot uh, by using uh, reinforcement learning training in simulation and then using to it. So um, this is kind of the pipeline that we use. So we first leverage the AMAS dataset, which contains a massive aggregation of all kinds of motion capturing dataset that kind of uh, a lot of academic labs or industry collected using mocap systems. So these kind of datasets contain mostly body motion, which is parameterizing simple, but also sometimes it contains the hand pose estimation. So which is parameterizing simple acts, which includes a model description of the hand pose of the human. And we then do some retargeting because humanoids have, much fewer degree of freedoms compared to humans. So we directly take the degree of freedom that humanoids have on their hardware and directly copy the joints from the joints that the humanoids have that is embodied in the human parameterizations. And given this kind of information, we design the reward function that we need to let the humanoids shadowing the human motion. So it includes encouraging the humanoids to match the target velocity and also the target joint position and target root position, while trying to save some energy and be alive. By alive, we define the humanoid. It cannot hit the ground, or it cannot reach certain threshold that is very low. Um, so and also we use a very uh, you know policy architecture that can adapt according to the proprioceptive history, and this kind of transformer-based policy send the joint position set points to a PD controller that runs at 1,000 Hz, which will be converted into toys. So I'll first show some demos of the shadowing policy.
And Zipeng, just to clarify for these videos, the ones where the robot's typing or something like that, or playing the
Yeah, that's all
piano.
shadowing right now. Yeah, so all the compilation videos here are there's a human like standing beside or behind to tally up the robot.
Okay, and for those ones where the robot's interacting with an object, is the human also interacting with, especially with fine control like the keyboard and the is the human also interacting with the same type of object?
We can try, but we don't actually do that. Yeah, maybe that's helpful, but like we didn't really do that. So it's mostly like, if the humanoid is playing a guitar, the humans are actually playing just air guitars.
Got it. Thank you.
Yeah. So during deployment, we kind of use this pipeline to let the humans tally up the robot, tally out the humanoid. So first, we use like single RGB camera and an algorithm called WAMP for body pose estimation. So it runs at around 60 hertz and capture the body pose and the hand pose estimation to get a simple X parameterization of human bodies. Yeah, also, we use another algorithm for the hand pose estimation. After we got the human parameterization of the human body, we do the body and hand pose retargeting so that it can match to a humanoid mythology, which have much fewer degree of freedoms. And then given this target pose, we send this target pose to the policy, which is the transformer that we train in simulation, and it can actually output the target positions to control the robot to let the robot trying to match the human pose, and meanwhile still standing and prevent the hardware from falling. And we did some user study and also analysis comparison with other teleoperation systems, in the sense that we found that when controlling the humanoids, our shadowing system or vision-based shadowing system requires only one operator and its whole body. This is very different from all the baseline methods that we compared to. For kinesthetic teaching, the cost is also pretty low. You just need a RGB camera for the hand pose estimation. But in order to holding the humanoid while trying to move its arms and the hands of it, it's very difficult to just perform it with only one human operator. And also, it cannot do whole body control given this kind of kinesthetic teaching approach. Compared to ALOHA Quest, the cost of our one single RGB camera system is much cheaper, and also they require more than one operator to perform all the tasks because it requires one person for the hand pose estimation to control the humanoid hands, and also requires another human operator to control the arms of the humanoids. And we didn't find it easy to do whole body control given these other two teleoperation methods. So we also did some like robustness tests in the sense that we found like we pushed the humanoids around when standing and found the maximum threshold for the humanoid to standing still given our policy, which is much larger than the default controller that the manufacturer shipped. And we also our low level policy demonstrate the whole body skills that is needed for tasks like squatting, jumping, and standing up. When trying to apply to real world scenarios, one thing we actually want the humanoid to achieve is that it can do all these tasks autonomously. At the same time, we already set up like a pretty good teleoperation system that humans can control the humanoid to perform all kind of tasks. Given that kind of teleoperation shadowing feature, we can use a humanoid to collect a bunch of data and collecting the images, collecting the actions that it takes to like serve as the input and output peers for the supervised behavior cloning training. And compared to previous method, we add kind of a forward dynamics prediction loss to prevent the policy from overfitting to proprioception, and we found it to be very useful. And the second feature is that we use a binocular perception for the depth scientific task. So instead of just mounting one RGB camera on the head of the humanoid has two RGB cameras, one on the left and one on the right, serving as given we don't do explicit serials for the depth estimation, but we just fed in two images to the transformer. So kind of doing the implicit serial for depth estimation. So I'm going to show some autonomous skills of the humanoid. Yeah, so these are the autonomous skills the humanoid can do after collecting several demonstrations. So we did some comparison study, how data efficient and how the performance, the success rate of you know different imitation learning methods or different control methods work for the humanoid. We compare with ACT and the open loop controller, which just replay the recorded demonstration of a human. And also we compare with some monocular based HIT solution. So in all of the tasks that we tested, we randomized the position of the object that the humanoids gonna interact with, and we randomized the initial positions of the humanoid. So, so that's why I kind of explain why the open loop controller doesn't work in the most cases where the performance of basically zero. And for the monocular baseline that we tested, the performance is severely degraded in depth-sensitive tasks like folding clothes, where the humanoids actually need to, precisely place its left and right hands in order to grasp the left and right sleeves of the sweatshirt. Um, when uh, when the humanoid is just using a monocular vision, the kind of pretty it's not very good at estimating depth. So sometimes when it's trying to, grasp the last sleep, it exert more force than needed. So push against the tabletop and destabilize itself. That's why the performance in the folding clothes task monocular baseline has a very low success rate. For other tasks like tying shoelaces, wear shoes, and walk, ACT and binocular have pretty low performance. That's kind of due to the overfitting problem. That without the recognition on the forward dynamics prediction on image features, ACT kind of overfit to a behavior that is focused on the proprioception without noticing the very small details that's involving the position of the shoelaces. So yeah, some key takeaways. We found large-scale RL is very useful for training a task-agnostic low-level policy. And we use that for teleoperation, which is very low-cost and intuitive. So given the data collected through teleoperation, we did imitation learning in real world for task-specific learning of autonomous policy. So we kind of combine two ways of learning. One is imitation learning in real world for task-specific learning, and we combine that with large-scale reinforcement learning in simulation and sim real for task-agnostic low-level like motion policy. So yeah, so that's it for this project, and I will switch to MobileAloha and briefly discuss about that. Oh, is there a question?
Hi, can you hear me?
Yeah.
I'm wondering if so do you find having teleoperated them using both like the arms and the camera, do you find that you have more precision with either? Like, can you be more precise with the arms and the grippers?
I mean, there are definitely ways to improve it. Like if we use a multi RGB camera system, that's definitely more precise. If we kind of use a mocap system, that's definitely more precise. Or instead of relying on the RGB post estimation, we can just ask the human operator to have some kind of device, either a glove or a VR handle or VR controller. It can hold in hand and will be more precise. But yeah, so what we trying to do is there's definitely key advantages of using just a single RGB camera for post estimation because all the videos online have just
Right.
one camera playing. So if we can leverage the system for tapping to the passive data set, massive large scale data set online, then it will be great.
Right, I see. Thank you.
Thanks. Yeah, I will try to briefly wrap up the MobileAloha presentation and then answer the question. Yeah, so this is a kind of a very different project in the sense that it's still aiming to be, build a general purpose robot for all kinds of applications. but it's not a humanoid. It's wheel-based, and kind of it's more like humanoids on one end is like very integrated system, needs a lot of care in the hardware design and support. But MobileAloha is on the other end. It's wheel-based. It's more like people can assemble it by themselves and get whatever components that we can to make it low cost and do the be as dexterous and mobile as possible. And this is how we do the teleoperation. So basically, the human is tethered to the robot itself, and it's holding the puppeteering arms for the actual robot arm that's interacting with the environment. By this, we capture the arm motion information of humans, and also the base information, the movement information of the human. So the hardware has two kind of setups or configurations. So on the left, we show the teleoperation config of the robot. So it contains not just the robots itself, but also the teleoperation mechanism that is on the back of the robot. And we put the like a battery pack and also the laptop on board. It serves kind of like the onboard power supply and also the onboard compute for the network inference and for data collection. Through deployment, we kind of detach the teleoperation mechanism, and the whole setup can be more compact and it can navigate more easily in a narrow, cluttered indoor environment. Some key specs. So we are using a differential drive, so it's very easy to back drive the robot by tethering the human to the whole setup. And so as a result, the total number of degree of freedoms is 14 plus 2. So the 14 is 7 off each for each arms and 2 degree of freedom for the base. So although the weight of the robot is around 75 kilos, which is around 150 pounds, it seems pretty heavy, but when we try the human operator trying to push the robot around to collect data, the resistance is pretty low. So we measured the resistance on the vinyl floor, and it's only around 13 newtons. And yeah, we collect around 300 trajectories in total, and which is around 50 trajectories for each task. And we also did some like user studies. We found MobileAloha is pretty easy to learn to teleop and use them to perform tasks. So for each task that we tested, after 5 trials each, an average user that have no prior experience with teleoperation can learn to perform the task, and on average, it can approach the speed of execution of an expert after 5 trials. So the expert here are the author of this paper. And we open source everything, including the hardware, and people feel free to check it out to include all the details to build the hardware. And there are many manufacturers right now are manufacturing the hardware setup, and people are ordering on these platforms as well. So after data collection, we need to find a way to use the data. So we take a very similar architecture as the original ACT, in the sense that right now we're taking only 3 RGB cameras, 1 head cameras, and 2 wrist cameras as input to the policy, and the decode action sequence that can be executed like for 25 actions in half a second. And we also found the efficient policy and VIN work for our setup. So I'm going to show some autonomous behavior of the robot that it can demonstrate after training. So we can also do some, human interaction tasks. And in this task, we only collect the data for, training, pushing the chair inside for 2 chairs. So when we trying to run the policy, it doesn't stop at the 3rd chair and continue extrapolating to 4th and 5th chair. So one trick that we use to improve the data efficiency and performance of the policy that we train is adding a co-training term utilizing an existing data set, which is we get from the static ALOHA data set. Because they don't really have the action of the base motion, we just set the base motion, in this case, to be 0, which kind of makes sense because all the tasks of static ALOHA doesn't really require, the work cell to be moved around in order to perform the task. Yeah, so in co-training, we include around 800 demonstrations, and from a different set of tasks, and we sample with equal probability from the MobileAloha dataset and the static ALOHA dataset, and yeah, and it turns out to be very useful in improving the performance. So in all the tasks we tested, co-training actually improves the performance of ACT. And for several tasks that require fine manipulation, like rinsing a pen, or calling an elevator that require pressing the elevator button, it actually turns out to be crucial to include the large amount of data that we have from all kinds of tasks that collected for static ALOHA. And it's pretty compatible with all kinds of SOTA imitation learning algorithms, and not just ACT. And we did some data efficiency tests, and it turns out co-training significantly improved the performance in low data regime. So the curve co-training dominates the curve that does not use co-training. And we also test whether co-training is robust to different kind of data mixture, which is in the past turns out to be very brittle in many other applications like training large language models. In our case, it turns out to be not quite sensitive in the sense that we tried 30%, 50%, 70% of different co-training metrics, and turns out the performance is pretty robust to that. And we also compared the co-training with pre-training in the sense that we pre-trained the network with only static ALOHA datasets, and then fine-tune with MobileAloha dataset. But it turns out it doesn't work that well, either because of overfitting or other catastrophic scaling mechanism that we don't really understand right now. And the co-training has a much higher success rate, better than the pre-training method, and method that just train from scratch using only mobile dataset. And we also did some robustness tests and repeatability. We randomized the position of the initial position of the robot in the case of calling an elevator, and we randomized the position of the object the robot is gonna interact with. In the case of wiping wine, it's the position of the wine glass. It turns out in all cases the robust the policy is pretty robust to all kinds of disturbance and all kinds of disturbance of the objects and initial position of the robots. We release the code and also the code commit histories, so people also feel free to check out. Basically, there are a lot of methods that we trying to use, but it turns out not to be very useful. And in the end, we kind of roll back to the simple recipe of using code training to improve the performance. Yeah, so I think that's it, and very happy to answer more questions in this case.
Thank you so much for that, Zipeng. I appreciate it. That's great. Okay, so for questions, could you please just drop your questions in the chat on the right, and I'll select questions based on a couple of priorities. So uniqueness of the question, relevance to the actual content here, rather than more general questions, and first-time askers. Put an asterisk near your question at the start of your question if you want to unmute and speak. So that just gives most people the opportunity to just type their question, have it spoken for them by me, if they prefer not to unmute or they're not set up for that. But okay, so to start with, there's a question from Guo Li and from Ram, and actually, can you, yeah, Zipeng, I'm just going to pin you so that you're there.
Yep. Okay.
Okay. Your pinned now. So and from Ram as well, because they're quite related to each other. And if I may paraphrase is, how do you think, what do you think the best way is to now take techniques that you've developed in HumanPlus and leverage the internet of data, like YouTube, for instance, or whatever's out there in terms of videos?
Yeah, that's a good question. The short answer is that I don't know at all. But you know, if we're trying to do that, then it can be pretty good source of pre-training in the sense that all the kind of YouTube data that contains a human performing task, we can use the same pipeline to do the pose estimation of the body pose, of the hand pose. And then, you know, given that, and given, you know, the RGB that capture the scene information and the metadata that capture the, you know, task description, we can leverage that as a pre-training to train the imitation policy that we currently have for, you know, specified only one task. Maybe that's a pretty good initialization for, you know, a general fine-tuning mechanism. Or even better, if, you know, the whole pipeline works very well for precision purposes and robustness purposes, then, you know, we can maybe in one day train a generalist policy that, you know, takes in the RGB images as input and also the task description, task input, and then the output of the policy control, you know, given sending the output to the low-level policy that can perform all kinds of tasks using one generalist policy. Yeah, so that's something that's pretty interesting to you know, pursue as a, you know, way to tackle the robot data scarcity problem.
Okay, and just to double check, there's nothing specific or particular about your RGB camera setup that, oh well, we can't use these YouTube videos because they have like a, you know, different type of camera, different like camera matrix and stuff like that, right?
Yeah, so the hand pose detection algorithm and the body pose detection algorithm are very robust to all kinds of intrinsic that we train. So we don't really calibrate the RGB images to, you know, look certain way. And yeah, the algorithm is trained to be robust to all kinds of intrinsics of camera. So that should work for quite well for different kinds of videos online.
Okay, great. Now, Thomas asks, how much latency does the shadowing system have, and does it hinder the human demonstrator from dynamic behaviors? I think you had like a video of like playing ping pong, right?
Yeah, that's a good question. So, so latency really depends on how good you engineer the system. The most kind of, there are two parts of latency. One is network latency that transfer the commands from the workstation to the humanoid. So it's either through wireless, like Wi-Fi, or maybe Bluetooth in communication. In this case, we use Stanford Wi-Fi, which is not that great in terms of latency, like low latency communication. And the second thing is the HumanPlus real-time estimation. So we use a 3090 GPU, which is also not that great like GPU for like low latency network inference. So if you optimize these two factors really well, like using a H100 and then do some quantization or optimization of the model, the human pulse detection model, then the network inference latency can be very small, and also the network communication latency can be reduced by using a better router or better communication protocol.
Great. And just to tie off the second part of the question, I mean, were there any situations in which you did your best in terms of reducing latency with all these methods that you said, but there was a particular task that the latency was too large for you to be able to do it reliably because it was dynamic, relied on really quick reactions to changes in the scene?
Yeah, that's yeah. So for any dynamic task, the lower latency, the better. For example, if we were trying to, I would say, fling a quilt or a bed sheet, or trying to toss something with very high controllability, that is pretty hard. So if the latency is like around 0.5 second, then all the thing we can do is just open loop control and trying to, like muscle memory the motion that the human should do. And there's, given the high latency, it's pretty hard to do all these kind of dynamic tasks. But if we have a lower latency, that let's say if we optimize the network communication and the network inference speed, then it will be much easier to do these kind of dynamical tasks.
Okay, thank you. Vil asks, so I think you had like a slide on comparing like the data mix ratio between co-training data and the actual task data, but actually Vil asks, does the size of the co-training data set matter? Like, does it stop improving performance at some point? Like, is there a limit to like how big it is? So he's talking about numbers like 50 task specific episodes and 1 million co-training episodes. Or do you not need to go beyond 1 million or even up to 1 million?
That's a good question. I haven't tried because there's no 1 million high quality robot data for data trajectories out there. Yeah, we don't know about that, but the general idea is that if we have that kind of massive amount of data, then it definitely helps the generalization in all kinds of tasks and understanding of different task descriptions. Yeah, but no one has tried that before.
Good.
I would say like one project that's similar is RTX, but yeah, that's kind of focused on more tabletop manipulation and also single arm manipulation, more like a pick and place kind of task.
Right. Thank you for that. Gigi asks if you've, I mean, there's a lot of data out there, but have you considered using text to video models, or do you think there's any value in using text to video models like Sora, for instance, to try to quickly generate a broader training data set, maybe to do some tasks, maybe for specific training that you can't easily find videos that show that task well?
Yeah, I would say definitely if we have a perfect word model, then that can serve as a real world simulators of or render of the things that we can do. So we can do either planning from it, using it, or generating a bunch of data and training, using it to train together with the robot data that we have. But yeah, I'm not sure how to do that in the sense that there is little access to the perfect video models, and yeah, and right now the video models still hallucinate and don't really have a pretty good physics.
Yeah, that's right. I mean, we can't have arms morphing from one side of the person to the other, because I'm sure your humanoids can't do that. Xiaolong asks a very practical question. For the clothes folding tasks, just considering like a certain type of clothes, like just like the same shirt, how much data do you think you need to like what sort of scale data set do you need to have to gather to be able to reliably fold that shirt from all sorts of initial positions? I might extend that question real quickly as well. If you can answer a second variant of it, which is does the answer change if you have co-training with a lot of other clothes folding data sets?
Yeah, that's a very good question in the sense that right now we randomize the position of the clothes of the sweatshirt, and we kind of randomize the angle placement of the sweatshirt, like up to, I forgot, 10 degrees or 20 degrees. And that's only for one shirt. So we collect around 40 demonstrations for that, and it achieves like above 80% success rate. But yeah, that's like, it's pretty hard to define what's by solving a task means, right? So even for folding one sweatshirt, there is a success rate. So the data required for folding like up to 90% or 95% or 99 or 99.99% is very different. So the data requirement, the quantity that we required in trading a long tail, pushing for very high success rate, we definitely require much more data. And the second thing is that the quality of folding also plays a role here. If we want the humanoid to perfectly fold the sweatshirt to a perfect square, or without any wrinkles on the shirt, then it's pretty hard. Yeah, but if we just wanna somehow the humanoid fold the shirt, and maybe we don't care about whether the folding is perfect or not, it just complete the task, kind of complete the task with 90% success rate, and 100 demonstration definitely enough for that. And co-training can definitely help, I think, in perception, but there's basically no humanoid data set out there like performing similar tasks at a similar, given a similar morphology. So whether that will help significantly, I think requires more experience.
Thank you. Marcos asks an interesting question. So, like, what's stopping from using, like, so you have like the third person videos for training the low level policy, and then you have the egocentric videos for training the imitation learning. And Marcus asks, well, what's to stop you just from using third person for training the imitation learning? Because then that lets you actually leverage all of YouTube, even for the imitation learning side of things, not just the low level RL policy.
Oh yeah. So yeah, that's a good point. So in the sense that we don't really test it because it's just cool to have everything on board, and all my past projects using sensors and compute and power on board. So I just want to put everything on board. There's nothing prevent we just use a third person camera and use that as a quote unquote vision for the humanoid, and we can definitely do that. And it's actually as he mentioned that it's even better pipeline for using the YouTube dataset that I mentioned, because most of the YouTube dataset are third person camera. You are using third person cameras. So yeah, that's something to consider in the future.
Okay. Prakar, I see that you have a question about transferring across different embodiments. Well, I'll read it verbatim, and Prakar, if you want to unmute, you can, because I'm trying to understand it myself. So in the context of data collection for humanoids and mobile manipulators, how transferable is data across different embodiments? Specifically, can data collected from one embodiment effectively generalize to another? Additionally, if we mine extensive data with a third distinct embodiment, how beneficial would that be for advancing capabilities in other humanoids or foundation model systems?
Yeah, I think the only experiment that right now we have is like kind of similar, a line of work that's similar to RTX. But yeah, it's an open question. I don't know. Yeah.
Yeah, thank you. Alec asks about if you've thought about force feedback for complicated tasks like or contact-rich tasks like shoelacing or cloth folding. If you think that would be beneficial, if you think you could incorporate it somehow into this HumanPlus idea, or if it's maybe incompatible.
So what? Sorry, I didn't really get the question.
The question is, I think I paraphrased a bit too much there. Maybe the question is one liner. Would shoelacing task or cloth folding task policies benefit from force feedback?
Oh, okay. Yeah, I think that will be the case in the sense that it prevents it's a pretty good indicator of whether the fingertip actually grasping something, or the position of grasping, or the like precise or robustness of the grasping. So yeah, I think that definitely force feedback or tactiles can provide that information. So if we incorporate that into the policy training, then it should provide better performance if we incorporate that modality.
Great. So there are no more questions from the audience. We've still got a little more time, so I'm waiting for more. Oh, hold on. Marcus has asked another one. These problems with hardware tests. Yeah. So what are your biggest? Yeah. Okay. You can read the question, or actually, I'll read it in case the YouTube video comes out and there's no text on the side. What are your biggest problems with the hardware you tested so far?
I see. For the humanoid, it's like definitely right now the H1 has 19-degree freedoms. If we have more degree freedom, then the humanoid can do more agile motion, then it will be great. So it can shadow the human more precisely, or it can perform tasks more more whole body tasks more easily. And for the MobileAloha, I think right now the capability is definitely there to do all kinds of tasks that we tried. That I tried in home for all kinds of home tasks. But if we have a hardware that has a lower occupancy, meaning that the space it occupies is much smaller, then it will be great. So one of the arguments for using humanoids, or all kind of humanoid company are arguing that humanoids have a much lower occupancy compared to wheel-based robots, and it's kind of they argue that it's useful in indoor cluttered environments like home environment that the humanoids need to move around. So yeah, so.
Great, thank you. Alec wants to know, what did you do specifically to help a robot recover from human interference, like the pushes and the kicks? Because you showed that diagram before where your robot can recover from even greater forces than the shift controller that came with the robot. So did you have any secret sauce in your policy or your training?
We don't. So for that task, we measure the maximum force we can exert on the robot waist that will not result the humanoid into moving. So they don't really, it actually definitely, if we push harder, it can, in the humanoid will like stumble and recover from that, given the low level policy.
Okay, and I kind of
so-
stole the question from Alec there because I paraphrased it. So his question specifically was just, what did you do to help the robot be able to recover from human interference?
Yeah, we don't really do anything special. So it's just a policy handles the recovery. Everything is kind of emergent during the training. So in training, we specify the robot. It's not a specification, but it's like reward specification. We encourage the robot to not fall in the sense that when it hits the ground, we can detect it in the simulator, whether there's a collision or not. If there's a collision, we just kill the trajectory. So the RL agent or RL policy cannot get more returns from it. So we're trying to optimize to control the humanoid in a way that it will not hit the ground or do any self collision. And also we like specify the reward such that we ask the policy to match the human reference trajectory as much as possible. Yeah, we also randomize the environment to incorporate all kinds of friction of terrain, and we use policy that takes in a history of proprioception information, not just one state-based policy, but it's more like history-based policy that it can recover from the previous mistakes or previous unstable behaviors given the observation.
Great. Okay, well, we're coming up on the end here, but I'll still the last question for myself. So you mentioned at some point that the depth, that having binocular vision was really important. Okay, this will be the second last question because Marcos really wants to make another question after me. So yeah, you mentioned that the binocular vision was really important for depth. So then my question to you is, how sensitive are we now to, this, like, how well calibrated or how static those cameras are? Like if we bump the robot and the camera slightly moves, now the depth estimation would be, would be different if you use like a classical depth estimator, which I know you're not doing. But yeah, how sensitive are we to that?
It really depends what's quote unquote classical depth estimation algorithm is. So most of the depth sensor that we use right now is based on explicit serials. So it takes in a pair of RGB images and do pattern matching, and then trying to make some correspondence between two images and then estimate the depths using geometry. But there's a second type of depth estimation, which is kind of using LiDAR for active perception. These are two quite different things. For the implicit or explicit stereos that we are mostly like using for inter-real sense, then it's kind of similar to just training, feeding the RGB cameras into the two RGB images into the policy, because the total amount of information that we can provide or captured is the same. So I don't see there's the benefit of using explicit serials. Maybe it's good for rule-based system, but yeah, in end-to-end system, I don't think there's a difference. Or maybe including explicit serials can actually hurt the performance. I don't actually know because I didn't do ablation studies.
So the question was, that's useful information. The question was just basically like, if you train a model with your current binocular setup, then someone bumps the robots and then the camera moves a little bit. Are you going to be in trouble then? Or is it robust?
Yeah, then definitely. If you even for human beings, if you moves the position of your eye, then definitely nothing will work. You will fall. And there's actually early experiments on kids that if you kind of trick their perception, their control will also fail at the same time. Yeah.
Right. Yeah, I mean, I was wondering if there's some sort of in context kind of learning where if you move the camera, it's still able to, because you augmented it at training time, or you move the cameras at training time. That, you know.
Yeah, that's a good question. If we have tons of data and then randomize the position of the eyes, maybe it will work much better. It's like domain randomization.
Yeah.
Yeah.
Okay, good. Well, thank you so much, Marco. Since you actually haven't posed that question, I'm gonna stop questions here and the talk, because we're at 6 minutes over already. Thanks so much, Zipeng. It's really insightful. I really loved hearing.
Hi, Alex.
Yeah. Oh,
Yeah.
yeah.
Sorry.
Oh, Marcos is chiming in. Go on, Marcos. Last one.
Should I make the question or?
Yes, please.
Okay, yeah, thank you. Okay, so thank you so much for the talk. And just to follow up to what you said before, because it's really interesting to me. I feel that there's two big limitations with the current implementations of ALOHA, both in the deployment of the policies and in the training. So in the current setup, we have the problem with the deployment that we cannot deploy on any different robot, and then also with the training, we have the problem you mentioned with the camera view. And I feel, what if we solve both of those problems? If we instead of training on the videos of the cameras, what if we estimate the, because at the end of the day, all we care about is the grasp, like what we call in maybe traditional robotics, just the grasping, right? So there's these 2 points of contact of our gripper with the world, and that's all that matters in the end, right? So and motion planning actually and trajectory generation is actually quite advanced, and it's almost solved with traditional techniques, so we can abstract all of that away. And in that way, what if we use as input to learner policy just the grasping position of any gripper, sorry. And then if that abstracts away the camera view, because we will just be creating a model of the object and where we should grip it, right? And that could come from an input that's third view or like egocentric gripper view, right? Okay, and yeah, I don't want to ramble. So if you understand what I mean, let me know your thoughts.
Yeah, I think that's a good direction to try. We haven't tried that because I'm not a motion planning expert, but yeah, I kind of like building a hierarchy and trying to extract things into low-level motion generation and high-level skill generation. That can be a very interesting direction to try. And in the past, like people try to use like neural network plus I forgot the name, but like motion primitives, where basically it's line of work that's produced generating low-level motion primitives from Stefano shell. That can be definitely interesting. Yeah.
Thank you.
Cool.
All right, thanks for that last question, Marcos, and thank you again, Zipeng, for the talks, for such good answers to these questions. And I had a great time in this. I think I speak on behalf of everyone else who's still here. So yeah, thank you, and everyone else, till next time.